Hello everyone, welcome to this webinar, Real-Time Machine Learning with Hopsworks. My name is Javier de la Rua Martinez. I'm software engineer at Hopsworks, and I'm going to talk about integration between Feature Store and Model Serving platform and how this is relevant for doing real-time machine learning. So first of all, it is important to analyze where business value is generated in AI and how it relates to operational capabilities in AI systems. So based on this, we can classify systems into different categories in which the greater support for operations, the higher business value they can provide, being real-time machine learning at the top of the highest value being provided. So we can see how companies such as Netflix, TikTok, YouTube do real-time machine learning. They build systems that provide predictions and recommendations in near real time. And these predictions are computed using contextual information such as trends or user preferences, the latest items that the user has clicked on, and these kind of things. So we can translate these categories into how often machine learning features in the system are being updated, and also how often predictions are being computed. And also, this directly relates to the integration between Feature Store and Model Serving. And we see that for real-time machine learning, a seamless integration between the online Feature Store and Model Serving, specifically for online inference, is crucial for the success of these kind of systems. So for a better understanding of the integration between Feature Store and Model Serving, we can have a look at how the data flows through the system. So from left to right, we see that data is coming from applications, data warehouses, is being processed, and new features are being generated from this raw data and stored in feature groups. A feature group is a table of features that are related to each other. And when you want to consume these features, you can use feature views. A feature view is a logical view of a set of features that might come from different feature groups. And you can use these feature views to get training data to train your models, or to get the most recent values of features to enrich model inputs in your prediction services. So a bit more in detail, basically you can ingest data into the feature store following two approaches, streaming or batch. And then when you want to consume your features, the feature view provides two different APIs, an offline API and online API. You can use the offline API to consume features in the form of files or data frames, which is useful for training your models. And you can use the online API to retrieve the most recent values of your features and enrich, for example, the model inputs at prediction time. So in the model registry, you will find the serialized files after your model training, and also you will find a serving code which translates to prediction scripts and transformer scripts. Predictor script defines how the model is loaded and how it will be run to compute the predictions. And the transformer script basically contains code that will transform the inference request coming in, and it will generate more rich features that will be later used as model input for making more sophisticated prediction. And you can basically create bundles of files, joining model files together with the serving code, and create model artifacts. These model artifacts can be deployed in prediction services. They will be run in your model server and generate predictions in an online manner. And also, it is worth mentioning that there is a component that will be deployed aside model server, which is the inference logger. And this component is important to ingest the inference logs generated by the prediction service back to the system. These inference logs contain model inputs and predictions, and this is important for two reasons. One, you can generate more training data set, or enrich the data that you have within the system, or two, you can monitor your models that are being in production by analyzing continuously the statistical properties of the model inputs and the predictions. On top of this, a system should provide more well-known capabilities such as versioning or keeping track of code changes or experiments and so on. And we will have a look at this in the next slides. But another thing that I want to point out here is that it is important as well for the system to provide a way to compare the performance of different model versions without affecting the model version that is being deployed, and also provide a way to gradually promote the best performing model version or roll back the prediction service to use a previous model version. So in the system, we can identify different pipelines. On the left, we see a feature pipeline in which we basically will process the data that is coming in and transform raw data into meaningful features. They will be stored in the feature group. Then also we have training pipeline. Here we'll use mainly the offline API of the feature view to get training data and generate or train new models. And also we have inference pipelines that will compute predictions using these already trained models for later use by batch applications or online applications. And then, as mentioned before, on top of this, the system should provide additional capabilities such as versioning of different concepts in the system, such as feature group, feature views, model artifacts, and so on. Also, it should keep versioning of code changes, for example, for the model serving scripts or the code used for processing the features in your feature engineering pipelines or to train the models as well. And additionally, it should keep track of, or it should provide tools for schema management. So an example of this would be, imagine that you have a deployment that is generating all the time continuously inference logs that are being ingested back into the system. If suddenly a new class in one of the input features is detected, you could potentially create a new version of a feature group and store the new inference logs there. And then later on, you could generate a new version of the training data with this data that has shifted somehow or that has changed over time, in this case by adding a new class to a specific feature. And then you will want to train a new version of the model that also learns the patterns and relationships between the labels and this new class in the feature and so on. Additionally, another capability that is relevant here is the transformation functions. So it's basically providing a way to use the same code that transform the feature that end up in a training data set and the one that end up as a model input for making predictions. So by registering transformation functions in the feature store, you can reuse them in the training pipelines and also in the inference pipelines. And in this way, you can avoid what is called training serving skew. And finally, and also very important is to provide provenance and lineage, which basically means to be able to track predictions down to the features that have been ingested and from which feature groups are coming, which training data was used to train which version of the model, and so on. So having a closer look to the inference pipeline, we have two ways of computing predictions. Here we have on the one hand batch inference jobs that run periodically, and they will get batches of data using the offline API of the feature view and score this batch of data, or basically, compute predictions in a batch manner for later use of batch applications. And on the other hand, we have prediction services that deploy this model artifact containing a predictor script and transformer script that I mentioned before. And something that I didn't mention is the vector store. Vector store is basically a store for embeddings. An embedding is a dense numerical representation of an object or of an entity. It basically encodes information in the form of a vector. And you can use vector stores to store and also to find similarities between different embeddings. So let's say you have already an embedding representing a specific item and you want to look for items that are related somehow to this item that you already have. You can use, you can perform what is called similarity search using the vector store to retrieve similar items. So coming back to the prediction service, in the transformer, you can use the online API of the feature view to get the most recent value of the features, and also you can retrieve embeddings or similar embeddings to one that you compute already to basically enrich the model inputs before making the prediction. And then just to point out again, as you can see, the inference logger will allow you to ingest the inference logs back to the system. It is connected back to the feature pipelines. If we have a deeper look at real-time inference pipelines, we can start with the feature store on the left. We have a bunch of features and already several feature groups, and we have 3 feature views that join and select and join specific features of these feature groups. And something to mention here is that the rectangles that are in blue color are the ones that are used or that contributes to the online predictions in this example, this diagram. So you can use feature views to get rows of features and then map them into embeddings and store these embeddings in a specific index or embedding space in the vector store. And then if we move to the right, we see that there is an online application that is sending a request. The request contains the feature group the feature 4, it is a primary key. Let's say that this is a customer ID. This request is handled by the transformer. The transformer performs a low latency lookup using this primary key and retrieve a feature vector. This feature vector contains the most recent values of the features with this primary key. So this could be, for example, the latest items that the customer ID that this specific customer has already navigated through. And then in the same transformer, you can map these latest items into their specific embeddings and use these embeddings to perform similarity search and retrieve candidates of similar items from the vector store. And then using these similar items, which would become the enriched model input, it can be sent to the predictor, where a ranking model, for example, will score these different items and then return back to the online application a list of most relevant items to this specific customer based on the previous interaction of the customer in the application. So there are two things more to point out here. One is, as I mentioned before, the inference logs. The predictor is generating continuously these inference logs, which are ingested back to the system. And there is another thing, which is feedback, or they are also called outcomes, which is basically information that online application should be able to provide to the system to give some insights about the performance of the model. So for example, if the online application sees that the customer is not really interested in the items that are being recommended, then this online application could send feedback back to the system saying that it seems that the recommendations are not good or not relevant to the user, and then the system might make some decisions from this feedback, such as, for example, training a new model version with more recent data, or trigger an alert that for some system operators could have a deeper look into. So now we can have a look, an overview of the recommendation systems for the demo that I will show after that. Basically, recommendation systems are information filtering systems that provide users with personalized information based on their preferences and different contextual information, such as trends or things like that. And if you look at the state of the art in recommender systems, they are classified in different ways. We have collaborative filtering that are mostly used user behavior. So we can see, for example, the picture on the right, in which items are being recommended to a user based on the behavior of similar users in this case. And then we see we have also content-based filtering, which is more focused on item metadata. So this is the case of the image on the left, in which items are being recommended based on similar items that the user might have already checked or go through. Then we have also knowledge-based filtering, which uses explicit knowledge that we have regarding user, such as, for example, the user might fill already a form saying what they prefer and what they not, or some constraints in what they don't want to get recommendations about. And also we have context-aware recommender systems that uses more contextual information, such as, for example, the season or a month of the year, geographical location of the user, these kind of things. And finally, hybrid filtering, which basically use a combination of two or more of these recommendation systems. So in recommendation systems, embeddings are quite relevant because they effectively encodes information and represent this information in form of a vector that can be easily used to find similarities or to compare with other representations of the same type of items. So if we look at the diagram on the right, this is an overview of the system that we will see later in the demonstration. Basically, there are two main components. One is candidate retrieval, and the other one is ranking. The first one, user ID is received and is used to retrieve some context and from the feature store, which contains basically user preferences, trends, or historical items that the user has bought already. And then this is encoded into an embedding that is used to look for similar items. And then the second component, which is ranking, basically scores these candidates to provide a list of sorted candidates based on relevance, let's say. So we can have a deeper look at the candidate retrieval component. We will follow a two-tower model approach, which works in the following way. There are two models. One is the query model, and the other one is the database or item or candidate model. The candidate model will generate embeddings given item features. So it will generate an item embedding. And the query model will generate an embedding using user features plus information about the items that the user bought previously, for example. And this embedding that is generated by the query model is called query embedding, and it can be used to retrieve candidates for items that might be of interest of the user. The way we look for candidates is using using similarity search. There are different algorithms for that. We have nearest neighbor search, which is computationally expensive, and we have also approximate nearest neighbor, which is more efficient than the previous one because it's approximate. And there are different implementations of this type of algorithms. In this case, we will use one that is provided in OpenSearch. We will see later. And the way we train these two models is basically we want that the dot product of the embeddings that are generated by these neural networks are close to zero or zero when the user item pair has no interaction. So the user is not interested in these items. And we want the dot product to be of a high value when there is actual interaction. So we can have a look at a case of real-time recommendations that we will see next in the demo. So in this case, there is a user that logs in, and we use the user ID to get features from this specific user, so preferences, and also information about the items that the user bought recently. We will compute a query embedding using the already trained query model, and then we will get some candidates using similarity search. We will enrich these candidates with more item features, and finally we will score the candidates using our ranking model. So the way this is implemented in Hopsworks is the following. There are two deployments. In the first one, in the transformer, we will enrich the customer ID with information about the user and also the recent items. And then in the predictor, we will use this enriched input to compute the query embedding. And then next, in the second deployment, in the transformer, we will use the query embedding to get similar items to get candidates using similarity search. And then we will enrich these candidates using contextual information from the feature store, which in this case is more features about the specific items. And finally, in the predictor of the second deployment that is running the ranking model, we will basically score these candidates and return back to the user the list of ranked candidates. Okay, time for the demo. Let's go through some of the notebooks. For the demo, we use data from H&M personalized fashion recommendation style competition that contains articles, customers, and transactions. First of all, we need to connect with Hopsworks using the Hopsworks Python library. Then we can read our data. We see that related to articles, we know the color, garment. Related to customers, we know the age, postal code. And related to transactions, we have the price, sales channel, and also an event timestamp. And time of the year is commonly a strong predictor, especially for purchases where seasonality is relevant. So we will try to map the month of this timestamp into using sine and cosine into circle units. So we can use them in our models. So for doing that, we will create two transformation functions. We have it here, and we will register the functions in the feature store so we can later use them when we generate new training data, and also during serving to map the month that is coming in the inference request. So after that, we can proceed to create our feature groups. We will have three feature groups, one for customers, one for articles, and another one for transactions. We can specify the primary key, and also that we want to the features be accessible in an online manner using the online API I mentioned before. After creating the feature groups, we can see them here in the UI and explore the different features. Wait, sorry. Then we can proceed with the feature views. We will create first two feature views using all the features that are in the feature groups of customers and also of articles. And then we can move on to the next notebook. In this notebook, we will create training data for the first model, for the candidate retrieval component. So first of all, we will get the feature groups that we have created. We will define a query selecting specific features from these feature groups, and then we will use this query together with the two transformation functions that we register to create a feature view that is called Retrieval. We can see here. Then we can use this feature view to generate train validation test splits for training our two-tower model. So this is this can be found in the next notebook, in which we basically get these splits here, and we define the architecture for our query model, also for the item model, and lately for the two-tower model, which basically is used to train both models at the same time. So we will fit our model, and then we can just save them locally and use the same Hopsworks Python library to connect with the model registry and register our models in Hopsworks by using the create model method. In this method, we can basically specify a schema and also an input example for our model. So after doing that, we can check the next notebook, in which we will create an embedding space for our candidate embeddings. So for that, we first need to download the candidate model, and also, the candidate model. Then also get our items, and then we will go through each of the items and generate our item embedding. And lately, we will use OpenSearch Python library to connect with OpenSearch, create our index, and go one by one through all the candidate embeddings and insert them to the embedding space. The next two notebooks, I will not go through them, but basically, in the first one, similarly as before, we create training data for our ranking model, and in the second one, we use CatBoost classifier to train a model that scores candidates. Okay, now we can see the last notebook in which we will create two deployments, one for the ranking model, another one for the query model. For the ranking model, we need a transformer and a predictor script. In the transformer, we will get a query embedding, we will search for candidates, and we'll enrich each of the candidates with information about the item and also information about the customers. And then we will send them rich input to our predictor. In the predictor, we basically loaded our ranking model, and it's waiting for scoring candidates that will be coming in the requests. So after that, we can proceed with the second deployment, in which we only need a transformer file, in which we will enrich the customer ID and month that is coming in the request with user preferences and last items bought by the customer. And we will send this enriched input to our query model that will generate the query embedding used later by the ranking deployment. So we can create both deployments using the Hopsworks Python library, calling the deploy method that we can see here. And now we can render a really simple UI with radio that will take a customer ID, as we can see here, and also the current month that we're interested to purchase something. And we send this information to the models, and we will get a list of sorted items based on the specific scores from the ranking model. So this is everything. I think we are running out of time. So thank you everyone for listening. And if you have any question, don't hesitate to write it in the chat or in our public channel, which is public.hopsworks.slack.com. And once again, thank you for your attendance.